Okay, next up to talk about communications architecture is Mark McGranaghan. Mark is the Vice President of Distribution and Energy Utilization Sector for the Electric Power Research Institute, or EPRI. He leads the teams responsible for EPRI's research involving technologies, systems and practices for the power distribution system and customer systems, as well as the related information, communication, and cybersecurity infrastructure and systems. Mark has been with EPRI since 2003 and has had a strong influence on EPRI's research in the areas of power quality, advanced distribution systems, and the smart grid. We are very grateful to have Mark here with us this morning. Mark, thanks so much for joining us.
Thank you very much. I'm delighted to be here. I was talking to Dan that did my high school and college time here in Ohio, and always remember coming to Columbus as the state wrestling fun time. I never made it actually as a wrestler, but I made it down every year, with the wrestling team to watch the good wrestlers. There's always a blast down here. But I'm a University of Toledo graduate, one of the few out there in the power industry that are kicking butt. So I try to keep track of what's going on here in Ohio, and of course the utilities here are very important members of EPRI. So EPRI is a nonprofit collaborative research organization for the utility industry, and we have a couple of initiatives that are very close to this topic, and I'll be highlighting some of the things there around the end-to-end architecture for the grid of the future, and a telecommunications initiative that's working with utilities across the industry on answering some of the questions that we were talking about with Jeff. I'm going to try to do three things. Kind of reinforce some of the messages from Jeff on the architecture, the importance of the architecture, the laying a foundation for interoperability and so on. And I want to dig into the communications infrastructure in particular, and as that part of the architecture and all the different technology options and platform options that are out there that are being considered, and they are different all over the place. So we'll look at what we're doing in our initiative, and then look at some examples from around the world of decisions that are being made in the energy industry around that communications infrastructure. And then we'll focus on some of the technology trends that are influencing what we're going to need to do with that communication infrastructure, because applications drive the requirements for that communications infrastructure and the overall architecture. I grabbed this diagram. I like to use it from Ontario. Now, Ontario, there's many different market structures out there. Ontario's a deregulated market that has an independent system operator and has distribution lines companies and has competitive retail companies. But clearly, looking at it even from the transmission operator point of view, the vision throughout the industry is that everything is part of that infrastructure. And you see that around the world, Europe, Japan, Australia, that the grid is the optimizing engine for all these resources that we have to integrate. And the communications infrastructure and the platform that allows the independent system operator in Ontario to see the role of the water heater in a consumer's house is absolutely critical. And the communications infrastructure that enables that, the role of the distribution company as being part of that equation is all part of it. So I think it's a good diagram for illustrating the interaction and interconnectivity between all these different elements. So we are working on, along with Jeff and Pacific Northwest National Labs and others, the DSPX project, around kind of looking at the architecture options and why it's important, and really for now just emphasizing that thinking through the architecture is critical. It is the basis for innovations. Anytime you have an open platform that you can allow third parties, university thinkers, data analytics companies to plug into that architecture with their unique solutions, you're going to enable innovation. It's a huge factor, and the more closed the system is, the less innovation that we're going to let kick in. I think that's probably the most critical thing. Things like cybersecurity also critical. much more realistic to implement cybersecurity in a platform that's well-defined and structured. So these are critical aspects of the architecture that we need to keep in mind. Challenges around that, I put them in these 4 categories. First of all, it's kind of everything comes together at the enterprise level. And we'll talk about that from a communications infrastructure point of view, but at the enterprise level where kind of all the data and decision-making come together, whether it's in the cloud or it's on a private network, that's where our applications need to talk to each other. Our outage management system and our distribution management system and our customer information system and our control of distributed resources that are out there, they all come together at an enterprise level. So building a platform with messaging between those applications and between the systems that are collecting the data for those applications is absolutely critical. The communications architecture and infrastructure enable that. So we have to define that communication infrastructure, and that's where I'm going to kind of focus today. And then as we get down to the device level, thinking about these concepts of open application platforms on the devices within that architecture, absolutely critical. Think of an advanced meter that's at your house that anyone can write applications for, so that it's a smart platform just like your smartphone, and we enable people to write applications to help do diagnostics on your air conditioner from inside your meter. So there's a lot of potential there. And that concept of an application platform basically applies to every smart device out there. Smart devices that are on a distribution system, your water heater could be a smart platform. The architecture has to support the interactions between those smart devices. So that's critical. And then we need to build in cybersecurity throughout this whole thing. So I think of those as kind of the 4 challenges of dealing with the overall architecture. This is very much a global issue. It's not about Ohio, it's not about New York or California. It's about Australia, the UK, Japan. Everyone is working on this problem, this issue at the same time. And we're coming up with many different solutions that all can take advantage of, if they're open, the same kinds of innovations. The same data analytics innovation that helps to do diagnostics on someone's air conditioner could work in many different platforms, as long as the platforms are open to enable that. Australia did a project that the report came out in 2014. I got a web link to it. It's a very, very good example of called Smart Grid, Smart City project, where they spent $100 million to implement smart grid capabilities in 4 different cities in Australia. And the summary report is very good. And I pull this one diagram out of it to just emphasize the architectural issues of defining the platform. It was throughout the report of how critical that is to enable the functions to be implemented, so that the IT infrastructure, the communications infrastructure, the cybersecurity requirements, lay that out first. On top of that are the sensors, the monitoring devices that gather all the data that work on that platform. And then we can work on using that data for applications to optimize performance and manage the voltage and control loads and provide flexibility in response to variations in solar and all those kinds of things. So kind of those 3 levels I like that way of thinking about the platform, the kind of data collection and data management level, and then the applications that build on top of that. Good concept. One thing that's kind of defining a lot of the requirements for this architecture right now is distributed resources. So we have PV, we have energy storage, we have the customer's ability to control their loads, we have electric vehicle charging that can be managed. These are all, we call these all distributed resources, and providing the value streams to those distributed resources to participate in the grid is the big challenge of the architecture. Getting that value stream to the smart inverter, if it's going to help control the voltage, what does that mean? How are we going to integrate it, and how is it going to work in terms of compensation, if that's something we're willing to pay for? Energy storage, even more of a big question mark in the industry of where is it, and multiple value streams. How do we take advantage of those value streams, and how do we compensate for those value streams as well? Those questions, and Beth mentioned that these are not policy things. These are policy things. Policy is right smack in the middle of this whole thing in terms of, what the role is for the utility versus third parties, and that actually influences the platform and the architecture itself. So they do come into play, and you have to think through it. So we use the term DERMS, Distributed Energy Resource Management System. Kind of, I think it's one of our big fun things to work on right now. And DERMS is really an interesting concept in that it really challenges the architecture, because the DERMS could be anywhere. You think of a microgrid is a distributed energy resource management system for a local set of loads and generation that maybe can operate separated from the utility. Your home energy management system is a DERMS for controlling your loads in your house, and maybe the PV, maybe your electric vehicle charging. That's a DERMS. DERMS could run from a substation. DERMS Nest, controlling thermostats all over the country, is a DERMS. So how are we going to integrate with all these different DERMS implementations in different layers, different levels of the system to take advantage of these resources? We talk in New York and other places about non-wires alternatives for investing in the distribution system. That means we have to be able to treat these distributed resources as the same way we would treat investing in lines and underground cable and transformers and new substations. And that means we have to integrate these management systems wherever they are. So this is a fun challenge that we have, and is influencing a lot of the thinking about the architecture that you see in DSPX and others. So for now, DERMS and distribution management systems, kind of two separate boxes, but obviously could be advanced distribution management systems in the future. Where the DERMS is and what it needs to do, big factor into communications infrastructure. Big factor. And we're looking at some aspect of DERMS. You might have heard of open field message bus. Some aspects are controlling things locally out at the edge of the grid. Some aspects are controlling things in the cloud, like Nest thermostats, and we'll talk about all those. The driver for these distributed resources and their integration comes from the continued penetration of distributed PV and solar, and central PV and solar. The more variability and intermittency that we have in our generation resources, the more we need capacity and flexibility resources to make sure that we maintain the reliability. And so, we're moving, a lot of times you'll hear in talks people referencing the fact that kilowatt hours are going to be free. The incremental cost of a kilowatt hour will be zero, but we'll still have to pay to make sure that there's resources available when we need them. So we have to pay for capacity. We'll have to pay for flexibility. We see that in Ireland. They have an initiative called the DS3 for delivering secure and sustainable electricity system, and it's all about introducing new market elements to pay for capacity and flexibility. There's so much wind in Ireland that the paying for kilowatt hours does not assure that the system will stay together. So they have to pay separately for capacity, and they have to pay separately for ramping capabilities to make sure that things can come online if the wind dies down quickly or trips off because the wind's too high. So they have ramping services that are in their markets. As soon as you define that you need that and there's a value for ramping, then that's something that someone's local water heater could participate in. And there's projects for that. If we can control, all of the heating in Ireland is water-based, is radiator-based, so there's a lot of thermal capacity in water. So there's probably enough flexibility controlling water heaters in Ireland to provide the flexibility to balance wind. Of course, we're looking at battery storage as well. But the point being that we need to enable distributed resources all the way down to the customer to participate in the needs of the grid if we're really going to have an optimum performing grid. So very important. And the driver is penetration of renewables. If you don't have, it's kind of the dilemma in New York as we go through the REV process in New York. It's great and it's really great forward thinking, but we don't have that much PV in New York. So the actual market for some of these flexibility and capacity services, other than in special cases like Brooklyn, Queens and things like that, is not there. So it's difficult to actually provide the value streams when we don't need it yet. But in Hawaii, the need is there. In California, it's getting there. In Germany and the Netherlands and Ireland and Japan and Australia, these are places to watch because they're already there in terms of needing the flexibility and the capacity to make the system work. So they're being forced to build the architectures to make it work. It's important to mention AMI. In this country and many other places in the world, the AMI, advanced metering infrastructure, is kind of the investment that we're building on. For a long time, smart grid meant AMI. When people said smart grid, they were talking about AMI. That's not really the case anymore. It's much bigger than advanced metering. But AMI is still a critical part of it, and maybe a platform that we can build a lot of these other capabilities on top of. If we build a communication infrastructure and an IT infrastructure for advanced metering, building distribution automation on top of that, building other smart city functions on top of that, very realistic. And those future applications, in answer to one of Beth's questions, what do we ask? Ask how you're going to enable some of these future functions, like using a water heater instead of investing in a distribution system on top of what you're proposing as your AMI infrastructure. How's it going to use that? Or do I need to build a new communication infrastructure? Or am I just going to use the broadband services that go to consumers? So those are some of the options that we're going to talk about here in a minute. But keep the AMI infrastructure in perspective with all of the other smart grid functions that we need to implement. I also think the open application platform is a very important concept for AMI. We're starting to see some movement in that direction from the AMI meter vendors, and I think it's very exciting. So watch for that, and that's something that you can think about what that means. There's many policy implications associated with that in terms of the data and how you're going to enable third parties to write applications and what the cybersecurity implications are for that. They all come into play, but the upside, like your smartphone, the upside is huge in terms of the new capabilities that you could enable for the consumer. So AMI is definitely an important part of this whole concept. So those are, background, but what are we going to do for the communications infrastructure to make it all work? This is the 6 parts to our communications initiative, and I think they're examples of things that you do need to think about. First of all, throughout the power industry, we're converting to packet-based communication. We have, in our protection and control, our SCADA systems, we've had serial communications infrastructure for a long time, the cybersecurity implications of that, and the ability to use technology that's just out there with IP-based technologies is very limited to take advantage until we actually switch to IP type of communications capabilities. And that means in our relays and control devices throughout the grid, converting our device infrastructure to work on an IP type of infrastructure. So and there's a lot of issues associated with that, with cybersecurity and our control systems and that come into play there. Once we've done that, there's a lot of different options for what we do in terms of the communications. We'll talk about the different wireless options and using commercial networks as for our purposes in the utility industry. The role of fiber is absolutely critical to think about. We have some guys in our IT group that work for the utilities that talk about the fact that we should design for every stationary facility having fiber. Eventually, that's going to be the way society is. So we should think about what that means in terms of our applications, and wireless will serve our mobile needs and electric vehicle needs and things like that. But it's not that simple, but fiber is an important question in terms of where that comes into play and how far that goes. The edge of the grid, the customer, the connectivity there, to kind of getting that last step, what is that, how does that fit in? And then, of course, on top of all that, the standards and best practices across those things are important. So let's look at kind of these 5 different categories across the top are different approaches that are being taken throughout the industry. All of these are out there. There's examples of all of them from utilities that are using these as kind of their foundations for at least the field, what we call the field area network, for getting out to devices on the distribution system, integrating customers. Kind of the first one is what most of the AMI implementations use, either wireless mesh systems or point to multi-point. Census is here. Silver Spring's example of the Wi-Fi mesh. There's many other examples. Wi-Sun is an alliance that provides standards around these to help make sure that equipment that you buy is interoperable under these structures. That uses unlicensed wireless spectrum for the most part. We can go to licensed. There's a block of spectrum that Salt River Project bought a block of spectrum there that they're using. I don't know actually whether CenterPoint's WiMAX system uses licensed or unlicensed spectrum, but there are examples of both. You can lease spectrum from companies like AT&T and Nokia that have spectrum, but then it becomes your spectrum that you have for your use. You can use these virtual network operator concepts, whether it's a mobile virtual network operator, and now we're starting to see this private virtual network operator concept. The Netherlands is probably the best example. The energy company there, Enexis, is implementing a private virtual network infrastructure with the help of a company called BroadForward that provides us software. And or we can just put cell phone SIM chips into devices and use commercial cellular. So there's a lot of different ways to go, and they have different advantages. You know, the type of spectrum, who owns the spectrum comes into play, who runs the network infrastructure, whether it's the cellular operator or the utility themselves or a private company, and who is managing the actual core of the network, are all factors that come into play in that. And where you are on that determines whether it's a big upfront cost or whether you're paying an operating cost to lease capability. All these work. All these work. We can build cybersecurity into all these. There are reliability implications. You can deal with some of that with contracts. Some of that is an example in Nova Scotia where the utility and the communications provider get together and manage the reliability of the network by putting cell towers on the same category as hospitals for restoring power, and try to make sure this network is reliable so that they can use it for the distribution system as well as customers' cell phones. There's all kinds of different examples across the board of the way that can work. Some of the things that we have to think about in terms of regardless of where we are in this wireless different options, that we can help with the industry is looking at, you know, if we want to actually purchase spectrum in this 700 megahertz area, we need to actually lay out all the standards for using that, because that's not the spectrum that some of these commercial providers are using. If we're using leasing spectrum in private LTE networks, we have some of the same issues in terms of we're going to become the providers in that case and manage that infrastructure. We have to have that expertise in-house and have our own standards. Can we get the data rates and the capacity that we need out of you know, mesh systems with new technologies? Very important question. And then just in general, operating in the unlicensed spectrum, what are the interference issues? If that's, we don't have control of the spectrum and more people can jump in, what does that mean in terms of what we can do there? If we're going to use commercial infrastructure, what does that mean? What's the quality of service, and what can we expect in terms of reliability in the different options under taking advantage of commercial infrastructure and sharing the network? This private virtual network operator concept was an interesting one, where the Dutch government basically passed a law saying that individual companies could basically own and manage the SIMs in devices. So create a network operation that then interface to the bigger network, so that there becomes an in-between. And so you will never, if you write a contract with one network provider for the communications infrastructure and you decide to change, you don't have to change the chips inside your advanced meters or your other smart devices, because you have a network in between that provides the interface to the overall network, and that's the software from this company brought forward, but provides more control of the devices that are in your network, but still using actual public infrastructure, fiber and wireless towers and so on. We're looking at low power applications for sensors and things on the grid, and what that means, because there's many devices out there that it's easier if they work with batteries. It's hard to find something to plug them into, but we still want the sensor data from them. So those technologies are very important to be able to plug into this infrastructure. And looking at the cybersecurity aspects is absolutely critical. I'd like to mention fiber. Fiber is something that we really need to watch and keep an eye on. I've mentioned Ireland. Ireland is a good example of the regulator and the government and the utility getting together and saying, if we're going to deploy fiber in Ireland for broadband connectivity for customers in Ireland in general, let's just get together and think about the best way to do it. And in there, they had gone through a lot of investment to replace the distribution infrastructure. They upgraded the poles. They'd been old, 50 years old, 60 years old poles. 10 years ago, they kind of upgraded the reliability of the whole distribution infrastructure, and that's the best place to put the fiber. Same thing that Chattanooga did in Tennessee. So they came up with an agreement of, we'll use the electric infrastructure to build the fiber infrastructure, and allowed the utility to create a joint venture with Vodafone to deploy that fiber and make it available to other communications providers as infrastructure, but also saving a couple of fibers for controlling the distribution system and coordinating with advanced metering, and becoming a resource that they can use for next generation wireless. So fiber gets out close to where the antennas need to be and everything else. So that's an example of something going on in Ireland. Of course, the Google fiber in this country is somewhat similar. Huntsville, Alabama, building the fiber network and leasing it back to Google, but at the same time using it to control the distribution system. Chattanooga built the fiber network themselves, not for Google, so they became the Google for being the communications provider for their customers. There's all different models out there. The business model and the technical model can be two different things, in terms of there's many different business models that can still enable that fiber to be a backbone for this grid optimization and grid functions. So fiber is a very important consideration. I think that one of the challenges that I'm most excited about is really enabling the customer to be part of the flexibility equation for the grid. Enabling the customer to get new services that help them manage their energy, be more energy efficient, provide services to the grid that maybe you get paid for, but it definitely enables the grid to operate in a more optimum manner. And that generally is going to involve, this Internet of Things concept. It's already there with thermostats. So Nest or Ecobee or, the many different smart thermostats that are out there are all infrastructures in and of themselves where the interface is at the cloud level. We have a project called the Energy Management Circuit Breaker. That's the device on the right there. That's a circuit breaker that goes in the panel in your garage that has revenue grade metering, has controllability for that circuit. It has a platform that you can write applications on, so you can do smart things right there on that breaker in your panel, and a Wi-Fi chip. So it connects to the Wi-Fi in your house and comes with cloud services to manage that data and allow you to look at that data, allow people to innovate on using that data to help you control your water heater, or control your air conditioner, control your electric vehicle charging, control your energy storage device, your Tesla battery on the wall, whatever. You could do all the management of that and control that in that circuit breaker. So you can think of it kind of going right around the meter. Now we got actually more information that you'd have from the meter at the individual circuit level, all integrated in the cloud at the enterprise level. So how are we going to integrate that? How are we going to make that part of the way we manage the distribution system? Here's a couple of waveforms, a little bit hard to see, but on the right-hand side at the top, that line is the voltage data from my house. So that voltage data is being uploaded to the cloud every 10 seconds, but it's also available instantaneously if we wanted to make a voltage management application that looked at all these devices that are in people's panels. It's a power quality monitor. That's a voltage sag that I had a couple weeks ago. And you could see how that individual device responds to that power quality event. Of course, you can manage your energy and do demand response. So this is just a little window into what's possible with the devices at the customer level and the challenges of integrating those. And the fact that it's just going to happen. Whatever you allow the utilities to do or how they play in this, someone's going to do it. This breaker will be available. Someone's going to write applications that work on that breaker and make them available to consumers. And if there's someone to sell services to, like PJM, they'll sell them. They'll aggregate all those water heaters and sell them into PJM. We would consider that the distribution company has to be in there because you're impacting the distribution system, and the distribution system may have value streams as well. So we really want to see everything integrated with that capability. One of the projects that we have to help make that possible is working with the Wi-Fi Alliance to solve a couple of problems. It works pretty well connecting devices into your Wi-Fi. You got to make sure that the connectivity is there, but you think of Alexa when you configure it, or a device like that, it creates a tunnel. You allow it to connect to your Wi-Fi network, and then it talks to the enterprise level at Amazon and creates a tunnel that Amazon can always talk to it directly. But it still works with your password on your Wi-Fi system. So we're creating an additional capability with a working group in the Wi-Fi Alliance that will kind of help with the persistence and the security of that connection between some of these devices that might have cybersecurity issues, so that this will allow a third party, might be the utility, might be some aggregator, other ones, to create a virtual private network to individual devices in the facility, in your house, and that are outside of the password. The customer will have to get on the internet and say, okay, I'm allowing you to do this. But then that water heater control would be connected right to a virtual private network with the utility that's managing all those water heaters, and it would be independent of have a separate password and everything on that Wi-Fi network. So this is a fun project that I think will solve a few issues. It's still the reliability of whether the Wi-Fi network in the customer's house is even on does come into play, but the ability to integrate devices through infrastructure that's already there in cloud services is getting better and better. So just to summarize, we do need to think about the architecture. We look at these technologies and the use cases of what we want to do and what the architectural requirements are for that. We need to build cybersecurity into that architecture from the beginning. what that means in terms of bandwidth and latency, as well as the actual technologies for encryption and detecting issues needs to be part of the design. The communications infrastructure is the enabler for that architecture to work. And there's many, many different options for that communication infrastructure. They all work with IP. So the end devices that plug into that communication infrastructure are the same, regardless of whether we build our own private network or use the public, system or whichever, use fiber or wireless mesh or direct point to multi-point. It all, the technologies can work in all of those instances, and there'll be different solutions for a city than there will be for rural areas, and the technologies at the customer can still be the same. So that's the objective. The applications drive the requirements. So you do want to look ahead at what are the applications that are going to have value. Where does additional applications for plugging into smart city functions, what does the electric transportation infrastructure look like? How's that going to play in our communication infrastructure requirements? Where does advanced metering fit in? What are we going to do for outage and fault management? Where do microgrids fit into that in the future? Where does energy storage plug into this? Energy storage has many different value streams. Some of them have relatively high communication requirements, and others can work virtually autonomously from the, with their own local sensing. So how are we going to have local energy storage play in the large market? And looking all the way down to smart devices in the customer and how they're going to play is an important capability. I like to, GE, John's here, and they have a term that they use. If you've had the GE presentation from their Predix folks yet already, then you would have heard this. But I think that a term that they have may become, like a Kleenex type of a term for the industry. They call it a digital twin. The digital twin means that up here in the cloud somewhere, there's a model of the turbine generator that's actually running in this power plant. And that the sensors that are there in the power plant are continually feeding information to this model, and you're continually looking at the way the model works and comparing it to the way that the real turbine is working, and that's the way you continually do diagnostics on that turbine. And I think that concept of the digital twin applies, we can apply that to everything. We can apply that to the customer and the customer's role in the grid in terms of providing flexibility services or energy efficiency. We can have a model of that customer in terms of how they're likely to respond to prices or respond to control signals, and then we see how they actually respond, and we continually refine that so that we can rely on that as a reliable source on the system. You can have a digital twin of your air conditioning motor or your water heater or your electric vehicle, and think about the communication infrastructure requirements and the sensors required to operate on this principle. Your entire distribution system, you have a digital twin. This is the way it's supposed to work. It's part of your cybersecurity assessment. When things are not exactly the way they're supposed to be, one of the questions is, has someone changed something that they're not supposed to change? So this concept is going to, I think this concept to become a generic concept, and you guys won't be able to, maybe you've already copyrighted it, I don't know, but I'm going to use it anyway. I think you think about it, and it enables a lot of thinking about applications that are going to have requirements associated with them. So I'm going to leave you with that at the end as something to think about for communication requirements in general. And I'll just thank you for the opportunity again.
Thank you very much, Mark. Let's begin with questions. Commissioner Conway, do you want to lead off here?
Well, real 40,000-foot question for you, Mark, which is, who is responsible for either establishing or making the improvements to what already exists to the communications network? Is this the utilities communications network that you've been discussing, or is there some extent to which it's not?
Yes. That depends on which model you choose. If a utility is going to build their own communication infrastructure and manage it, then they have to maintain the reliability of that. unless they, contract it. But the other option is if a utility decides that they're going to use fiber and wireless that AT&T or someone else puts in, and they're going to contractually, assure the reliability of that infrastructure, then it's that other entity's responsibility to maintain the reliability. We do see joint responsibility out there in terms of, because some of the reliability of a wireless infrastructure, for instance, is power to the antennas, to the towers. And the utility can influence that by making sure that the electric infrastructure to the critical elements of the communication infrastructure is as reliable as possible and is restored, and there's automation, and they may have backup generators, they may have energy storage to help assure that. So it can be joint responsibility even if the infrastructure is not owned by the utility. But if the utility is building a new communication infrastructure and putting antennas out there for their AMI, and they're going to use their AMI as a foundation for distribution automation, then that's going to be their responsibility to maintain that then. And both models are out there, and they both are working around the world.
Let me see if I understand the last point, that both models are out there. In both models, is the grid operator, the utility, ultimately responsible for making sure that one or both of these models are in place?
It's the grid operator's responsibility to kind of assure the reliability and security of the electric service. So they have to make some judgments about the reliability and security of the communication infrastructure is critical to that. So they have to make some judgments about what's the best way to do that, both economically and in terms of technology and capabilities. They may decide that other people are more capable of maintaining the reliability of that, and we can pay for that as a service, and that actually is better for everyone, and that works. That's in Ireland. That new company is not the utility. It's a company called Zero. It's a separate company. That company, Vodafone and the electric utility together, formed it, but it's not the electric utility. They're responsible. Zero is responsible for the reliability of that fiber infrastructure and making sure that it's available to the utility for their grid services as well. And everyone made that decision, the regulator, the utility, that we can make this reliable enough, with this infrastructure. In the Netherlands, they're using public wireless infrastructure, same as the cell phone you use for your cell phone, but layering network operations, private network operations on top of that. And so they're relying on the reliability of the public infrastructure as their basis of doing their grid management. So those are decisions that kind of you lay the cards on the table in terms of what are your mechanisms for assuring reliability, and are they adequate, and do we have any input to those, and can we control those in any way? Those are all the questions that need to come out. In this country, a lot of utilities feel like they need to own the infrastructure to make it reliable. I would say it's just a philosophy. But, there's cybersecurity, reliability of that infrastructure influences the reliability of the grid, and so they want to be able to control it themselves.
Well, if you are inclined to go the other route, the European route.
I wouldn't call it European, because in Europe you do see private infrastructure as well.
Yes. Well, I meant if you go the route where it's not owned and controlled by the utility, does there have to be a buy-in by the utility to go in that direction?
Absolutely. It needs to be a partnership. So, and that's I would say that the biggest hang-up for that has been cost. Of cost, and the fact that utilities want something, they want contracts for durations that they're used to their assets working. So utility wants a deal for 15 years for their advanced metering. No commercial provider wants to provide those kind of contracts. So those are not really technical issues, but they are issues. But that kind of thing is changing a little bit in terms of the market. So if we get past kind of those problems and new business structures for the arrangements, you probably see public infrastructure providing more of a game. We'll definitely see, and to integrate thermostats and air conditioning controls with the operation of the grid, we're going to do that in the cloud. The air conditioning interface is your Wi-Fi. That's already done. And everyone's already, that's the way they work. So that's not going to be built on a communication infrastructure that the utility builds. That's going to be an interface in the cloud. So we definitely are going to have both in the end. Some of our actual resources that we're controlling are already going to be linked into the public infrastructure. And we'll have to control those in combination with things that may be directly managed. Like maybe we decide we need to talk to smart inverters that are on big PV installations with our communication system for reliability and security. And then we get some of our flexibility from electric vehicle chargers that are connected to customers' Wi-Fi. See both.
Thank you.
Yep. Commissioner Johnson.
Thank you, Mr. Chairman. Just talking a little bit more about design standards. And this is, what I mean is different companies, smart meters, different companies, other communication architecture, being able to use it in the same manner. How does that come about? How does it?
Very painfully, but
And to hear, some of this has not come about. Is that correct?
it's definitely a work in progress in terms of standards. It always is, but partly because the technology changes faster than we can keep up with them with standards. So new capabilities are coming out, and we want to give those to people, but they're not in the standards yet. But, we have organizations like the WiFi Alliance that as they develop standards and test protocols for interoperability across these different communication technologies, and the customers write in their specs that they want things to work that way, to the extent that the test protocols are good and they really exercise things. You can have things in your standards saying you need to be compatible with this standard, whether it's 61850 or Common Information Model or Wi-Fi Alliance, and if you don't, there's always many different ways of interpreting the standard. So you have to make your test protocols as effective as possible at looking at the interoperability issues that you really need, and you actually test for those, and that's what's getting better. So as we kind of continually improve those, the vendors make sure that their equipment is compatible with those, and we're seeing that. So that is allowing you to plug in capacitor bank controllers on the same communication infrastructure that you use for your AMI and your, as we start now, smart inverters is one of the big thing that we're trying to take advantage of as a resource on the grid, and smart inverters have some complicated functions in them. So the standards for testing those functions and making sure they're compliant with some interoperability needs is one of our big challenges right now. We already write in the specs that you have to be compliant with these functions of smart inverters, but to actually test to see whether the function for voltage control in a smart inverter works the way you expect and the messaging works the way you expect is the next step. But that's moving forward. I think everyone is on board with it. Makes sense. There's maybe not everyone. There may be some that are, would like a proprietary solution and kind of be outside the standards, because they think they could be the Apple of the electric power industry. But I think almost everyone is on board with interoperability. Makes sense. It increases the value of their product and increases the pie for everyone. So the participation in organizations like the Wi-Fi Alliance to make the standards better is very strong.
One follow-up question. Often we find that people don't necessarily agree, but this is something that they, there's something that there's some group that ultimately decides this question.
It's almost always an alliance that is responsible for the testing. That's where the rubber hits the road, is you're compliant or you're not compliant based on the testing that's usually certified by some alliance. The Wi-Fi Alliance certifies Wi-Fi routers that they perform these functions the way they're supposed to be performing them so that your thermostat will actually be able to connect up with your Wi-Fi router. That we're not to that extent with all of the other communication protocols, but the Wi-Sun Alliance is in that category of kind of moving protocol by protocol and defining the test protocols to make sure things work. So it's not EPRI. We help develop the test protocols. We work on them with these alliances, but we're not a certification house. It's those groups that actually do the certification. It's UL from a safety point of view. It's these other alliances from the actual communication protocols and performance point of view.
Thank you.
Beth?
Just a quick question, clarifying on slide 10, wireless solution space, if you could flip to that. So you have, I just wanted to make sure I understood this slide. You have this line, this vertical line between the first three and the last two. Is that a demarcation for some reason?
I don't know why we have that line there, to tell you the truth. All those things, these things can work. It's, I guess, because on one side of that line, you really are relying on the commercial cellular operator as your infrastructure, as opposed to leasing spectrum that you own, so that your communications is just in your spectrum. You're actually sharing spectrum. Your messages are being mixed up with people's emails to the right of that line. That's, as simple as that. Your packets are going out there on the same fibers or wireless, spectrum as the public's phone calls and emails and stuff. So that's probably from a security point of view, one side or the other. To the left, you're always on something that you control, either wireless spectrum or physical. You might lease it, but it's yours. You're not sharing that spectrum with the public.
So have you seen one used more than another? Or do you think there's a pull towards one over another?
Like for AMI in this country, I don't know if anyone's on the right side of the line.
Okay.
I thought we should have had someone, we had the DOE's grants, that we should have had a project where we used public infrastructure and showed that we could make it work, but other places in the world, they are making it work. Chattanooga is an example where it's all mixed. It is essentially on the right-hand side of the line, except for they own it. So it's still theirs, but they are mixing their control signals and their AMI data with people's Netflix videos. It's going on the same fibers. So there are examples, kind of, but in that case, it's the same entity that is controlling the whole thing. But around the world, there's plenty of examples where it does work. In Europe, the general philosophy is the communications to the transformers that step down to the low voltage. So they have a distribution system, and transformers step down to, in their case, 240 volts. And that 240 volts goes out to a number of customers. They tend to use power line communications from the transformer to the customer. It's starting to become pretty standard in Europe. And the communications to the transformer, to that location, is almost always public cellular. So they really do use the public infrastructure for a lot of but it's like a backbone. It would be similar to the takeout point for AMI in this country, which also could be on public infrastructure. It would be kind of the last part would be the wireless mesh that you might own yourself, and you might still use public fiber or wireless for the backhaul of the data from the takeout points.
Real quick, so the left side is more expensive than the right side, the public? Is that typical?
the left side definitely costs more upfront because
Okay.
you're investing in something that you own, you're buying it, it's a
Right.
capital. Over the lifetime, you'd have to look at it, you're trading operating costs versus
I know there's
capital
lots of
costs.
considerations, aren't there?
It's a
Yeah.
lifetime cost issue, and that's another question is what is the lifetime? The lifetime keeps getting shorter for this technology because new technology is becoming available. So what should you use? NL, who was one of the first to do AMI in the world, deployed 30 million meters, and we're at the 15-year point, and they're replacing all of them right now. So 15 years was the number for technology obsolescence, or let's say, technology became valuable enough that it was worth replacing, the old meters. Even though they still work, they're still advanced meters. You collect data, the communication infrastructure is there. Now the communication infrastructure is better, the meters are better, there's more flexibility there that they can economically justify replacing them. Maybe these will be replaced in 10 years. I don't know. So, that in these questions of capital versus operating, the duration of the cost is a critical issue. So kind of looking at that and what the use cases are going to be down the road becomes an important part of the discussion with, whoever's doing this investment.
Thank you.
Commissioner Friedman.
Thank you, Mark, for the presentation. Question for you. The proliferation of distributed energy resource capabilities and management systems, the DERMS, as you alluded to earlier, can reside in the house. The communication path can be either through a meter, through an AMI deployment, or in the alternative, I'm assuming, can be direct between the consumer and the provider of the product and service that is in the marketplace at that point in time. On an individual basis, the impact of a direct communication between the consumer and the provider may be inconsequential, but as a product innovates and becomes more popular, it begins to aggregate. And as there is a proliferation of the product and service, the consequential impact on the grid becomes much more notable, even though the communication is, once again, between the resident or the consumer and the provider of the service. Do you have a view on when it becomes appropriate to have there's an underlying question of regulatory reach, I suppose. Do you have a view on when it becomes appropriate to reach behind the meter in a circumstance where the communication is purely behind the meter and not reliant upon a utility-owned AMI or
I do have a view on these things, so I'll just say this, my personal view doesn't represent EPRI, and because this can be a controversial area, but and that's one of the reasons why we're working on that Wi-Fi router capability to assure a secure and persistent connection to individual devices, because those devices, those smart devices, are already being connected directly to the cloud, and the aggregation and the flexibility and the management of those devices can happen real time in the cloud. Doesn't need the meter for that. Maybe this energy management circuit breaker, another example, that's on the other side of the meter and goes directly to the cloud. So anything that you can do locally with a home energy management system, you could do in the cloud. There's no reason why the home energy management system wouldn't be virtual in the cloud. The cloud talks to every device anyway, and you have the ultimate flexibility to combine devices and combining water heaters all over an area, or combining devices in an individual house, or any combination thereof. You can do that virtually in the cloud. And we need to build a system that enables that. To be honest, the meter's going to be a smart cash register. It's not going to be the gateway to those devices. It might be a very good sensor, and we have the green button standard for sharing data from the meter. Many meters have the capability to broadcast data into the house, and we have technologies that are using that data effectively and providing value. So I'm not saying that's not value, but the devices that are using that data are also probably connected to the cloud for managing of that information and taking advantage of it and doing smart things with it. So, the meter plugs into this architecture, but it's not the gateway. The gateway the gateway will be in the cloud. There'll be something doing local things like Alexa maybe will, control all your devices locally because it's locally on your Wi-Fi network. But Amazon will be watching to see if there's something more intelligent, or they could download a new capability to do that and may override it when the prices change to some new value proposition that we only get that information up in the cloud. So to me, getting everything connected reliably to the enterprise, every single device is critical. And that should be our vision. And that doesn't mean we don't do local things and having peer-to-peer communications happening locally. That also happens. But, ultimately, we can optimize things with the ultimate flexibility by bringing all the data up. That's not a universal opinion.
Well, very good. Sadly, few of us have to get to a meeting with our staff, and we said we were going to break at 11:30, so I'm going to shortchange myself and staff. I apologize. But please do ask
Sorry for the long
more questions.
answer.
No, it's okay. Please do ask more questions after if you have questions. So, Mark, thank you very much.
Thank you.
Appreciate it.